How's it going, everybody? Welcome back to our Cisco Enterprise series. In this video, we are going to be going through the iBGP full mesh requirements that are needed to be understood, like seriously need to be understood, when it comes to developing an iBGP design. And we're going to talk through some of the specifics, and we're then going to be looking at configuration examples of how that comes into play. I am going to be discussing partial mesh designs through like route reflectors and confederations. We won't be looking at confederations specifically in this video, but that will come up in a later video or later videos. Well, there's going to be a couple of examples we're going to have to walk through. But the whole point here is if you are dealing with any type of decent sized BGP. Now, I will preface this by saying that probably out of 12 years of doing network engineering full time, I'd say 25 to 30% of the customers that I've worked with. So let's pick a round number. Out of 500 projects that I've worked on, I'd say probably maybe 100 or so had some level of BGP that was necessary. Some way more than others. You know, I had several customers. I'd say the past 5 years, I've dealt with BGP a lot more than I did in the beginning part of my career. And of those, say, 100 customers that I've worked on, or 100 projects that I've worked on where BGP was involved, about half of them were very, very simple BGP deployments. It was something as simple as setting up a BGP peering to an MPLS service provider edge router. You're just doing a simple eBGP peering. There's a little bit of authentication with the password, and that's it. That's the extent of the BGP that you're going to end up doing. So, ironically, there were several job descriptions that I've read, and I could probably find some in my email if I was to sanitize where they're coming from and just have the job description pulled up, where it is extensive experience with BGP and or MPLS. And then when I would ask a question about that, because that's one thing about an interview where you do have the option of asking questions about the environment you're walking into. And the common question that I would ask was, okay, your job description says extensive experience with BGP and MPLS. Extensive could be very, very wide depending on the person that's writing it. Extensive to me means you know a lot about all the individual capabilities that BGP does. You know about BGP design, you know about BGP configuration, and you've looked through the configuration guide and you've looked at all, let's say, 50 different nerd knobs that you can turn, and you've turned them all. That's what extensive experience with BGP means to me. What does extensive BGP mean to you as the manager? And so then they'll have to give you their explanation. And I'd say probably a good portion of them, when I've asked that question during the interview process, has always been, well, every so often we have to stand up a new site, and we end up getting an internet circuit, and we get a lease line, an MPLS circuit. And the MPLS circuit, we are going to be doing a BGP peering to them. And I'm like, oh, okay. So the extensive experience comes into play with, do you know how to advertise a route into BGP? And do you know how to filter traffic? That's extensive BGP to a lot of people, because that to a lot of people is complicated. So, especially when you're talking to somebody that doesn't have or hasn't put in the amount of time that you or I are putting into learning how the technology works. So that could be extensive to them. So you and I, it's going to be like, oh, okay, so we're just scratching the surface for the most part. So in those situations, you have to be able to qualify what they want. Because you'll walk into the environment and you'll be like, okay, well, let me see your BGP environment. They're like, well, it's just on the edge. I've seen a lot of customers do that. There's nothing wrong with that. It's just one of those things where you have to know what is expected of you when it comes to BGP. And honestly, there's not a lot of customers don't deploy extensive BGP. Some others do, some others don't. So just keep that in the back of your mind when you're looking at understanding BGP in terms of what it does. So with that little rant and real world scenario out of the way, you and I are going to walk through BGP itself and what you and I need to be, what you will need to understand about BGP from a full mesh requirement perspective. So why is iBGP full mesh needed? iBGP performs loop prevention via route filtering. So iBGP learned routes cannot be advertised onto another iBGP neighbor. The iBGP requires either full mesh peerings, route reflection, or confederation. The full mesh examples are as follows. You have path diversity, right? So all BGP peers learn all possible egress paths. Optimal traffic flows. All BGP peers learn the closest egress path. And the path selection by default would be based on the IGP metric to egress router, also known as hot potato routing. In other words, you're going to route to the closest egress point in the network you can. So the concept of this is you're going to route to the outside of your network before you're going to route to the inside of your network. So if you keep the BGP inside your network, you're going to route through your backbone to somewhere else. That's what they refer to as cold potato routing. So you're going to hold on to it. It's not hot, right? You don't have to get rid of the route right away. And you can, make a good route decision based off of what you've got going on internally. Hot potato routing is, if you've ever hot potato, I mean, it's you may not get the reference, but something gets tossed to you and it's hot and you want to get it out of your hand as quickly as you can. Or they it may not be literally hot. It might be figuratively hot, like where you get tossed something and you want to get rid of it as quickly as you can. So, example, like musical chairs. If you were when you were a kid, like you'd have 9 chairs but 10 people. So you'd have to be going round and round and round and round, and then as soon as the music stops, you have to try to get a seat. Maybe you weren't quick enough, and maybe you got out. And the idea is the person that is left out, they have to get out of the, they're no longer eligible to play. That's the concept. You want to get rid of the route as quickly as you can, so you find the closest egress point to your network, and you forward the traffic out that way. Some of the full mesh disadvantages, and this is where I tend to talk to customers about their scaling options, is you have this n times n minus 1 over 2. And this uses the PEMDAS rule, right? So you have parentheses, exponents, multiplication, division, addition, and subtraction, right? So the concept is very simple. You have to do what's in the parentheses first, and then whatever's in the parentheses is going to be multiplied by this. So the concept is very, very simple, right? In this case here, we've got 10 times 9, so you've got 10 routers. So you take, and you can't form a BGP peering to yourself. So therefore, you automatically have to deduct yourself from the peering structure and the architecture. So you take, there's 10 routers. We can only form a peering with the other 9. So it's 10 times 9 is going to be 90. Divide that by 2 is 45. Same thing with these other routers, right? The concept continues to roll. So operationally, it's hard to scale because everybody has to have a peering to everybody else. That's a lot of control plane. So, and that also means a lot of the same routing information being shared with everybody else. So, unlike an IGP where you don't have to do that, you don't have to form a peering with everybody else. So that is going to be the caveat with this, because of the fact that you have that, you run into partial mesh deployments, partial mesh designs, where you don't need to rely on only one choice. You can do route reflection and confederation that can interoperate. So why would you do this? Well, the simple answer to this is pockets of full mesh for path diversity, intercluster route reflection for scaling larger designs. So a partial mesh design example is route reflection as an alternative to the full mesh. So one of the key components of route reflection approach in addressing the scaling issue is that the route reflector summarizes routing information and only reflects its best path. So I can receive, let's say I'm a route reflector and I have 10 edge routers. Each of those edge routers has connectivity to other devices outside of the network. Well, what's going to end up happening is I'm going to receive all updates from all of the route reflector clients. They're going to send the route updates to the route reflector. The route reflector is going to then determine the best path based off of its understanding and then forward those routes off. So if you want to know more about that, then you would have to dig into each router, and then maybe there's an alternative path that you want to take and stuff like that. But there are scenarios, specifically they call it add path, which allows and best external. So you can go and take and learn more than what you need to, and then you can make routing decisions on that. We'll get to that more when we get into more advanced BGP. But both the multi-exit discriminator and interior gateway protocol metrics may impact the BGP route selection. With certain route reflection topologies, the route reflection approach may not yield the same route selection as that of the full mesh approach. A way to make route selection the same is by configuring the intra-cluster IGP metrics to be better than the inter-cluster IGP metrics and maintaining full mesh within the cluster. We're going to get into full mesh clusters. We're going to take a look at a route reflector cluster as we get further along. It'll be once we have a full understanding of BGP and we've covered a lot of the individual capabilities, we've gone through the best path selection algorithm, we've done some filtering, and we've gone through most of the nerd knobs. Then we'll look at scaling techniques. But the reality of it is, in an enterprise scenario, you're never going to do that. I've never worked with a customer that has ever been so big that they need a cluster, 2 or more route reflectors, unless I'm looking at a data center specific example with a VXLAN EVPN. So it's the only time I will automatically, you're going to do 2 spines so you have diversity, and both of the spines are going to be route reflectors down to all the spokes, so all your leaf switches. So the other one would be on a very large scale DMVPN where you're going to have 2 hub routers. Well, each hub is going to be a route reflector. Beyond that, unless you work for a service provider, you're normally never going to have clusters of route reflectors all paired together, right? The route reflectors themselves are full mesh, and then the route reflectors go out and you pin so many peerings to each route reflector in order to get BGP to scale. So how you do that will sometimes be dependent on your design. So the actual funny part about it is every design you walk into, you're going to more than likely, and I've done this myself because I've had to be able to be deterministic and be able to give my customers a concrete answer. But like, okay, I demoed this. Like I stood up, 8 or 10 routers in a lab. 4 of them were route reflectors, 6 of them were edge devices, and I just simulated a whole bunch of connections. And this is what the routing design is going to look like. This is what we're planning on putting into play in the real world. This is what I'm going to demo in the real world, similar scale. This is what your output is going to look like. And that's how you really understand how BGP works in the back end, is by doing things like that. That being said, so the scaling techniques, route reflection, eliminates the need for full mesh. Only peer to the route reflector. Like the OSPF designated router or the IS to IS designated intermediate system, minimizes prefix replication. Send one update to the route reflector. The route reflector sends the update to its clients. It does not modify other attributes when reflecting routes. So literally, whatever you send the route reflector, it's going to take it in. Route reflection and loop prevention. So you have a loop prevention through the cluster ID. The route reflector discards routes received with its own cluster ID. It sets the originator ID attribute to the router ID of the route reflector client on routes received from the client. The client uses originator ID for loop prevention. Let me talk a little bit about this. So when we talk about loop prevention, there's this concept of iBGP versus eBGP when it comes to route reflection and the cluster ID. The concept is very simple. If I have a cluster ID of X and I want to form a peering to another route reflector, I'm going to do that. If they have the same cluster ID, they're going to treat each other as iBGP peers, which means they're going to drop the routes, right? A route reflector discards routes received with its own cluster ID. Therefore, it's an iBGP style relationship where you can change the cluster ID and use a different one, and therefore if you are forming a peering with another set of route reflectors, different cluster ID, what will end up happening at that point is you're going to be choosing a different it's going to be an eBGP path. So you'll receive it and then you'll reflect it onwards. So there's some scenarios that come into play with how that operates. The originator ID is going to be the router that receives the external route, right? It's going to receive an external route via eBGP. Its router ID for BGP is going to be set as the originator ID, and then that is going to be propagated up to the route reflector, and you're going to have a cluster ID and originator ID. The cluster ID is the route reflector that reflected the route. The originator ID is going to be the route reflector client that received the route update and then passed it to the route reflector. The originator ID is the router in your autonomous system that's a route reflector client that learned an external route and then propagated it to a route reflector. That's what that means. Route reflector peerings. In the simplest of route reflection designs, a central peering point is chosen for all devices in the iBGP domain, and all peers of this device are defined as clients. So here's some three types of peers that you need to be aware of. eBGP peers. Routes learned from eBGP peers can be sent to other eBGP peers, clients, and non-clients. When it comes to, so you can sorry, I lost my train of thought. Routes learned from eBGP peers can be sent to other eBGP peers, clients, and non-clients. iBGP clients, routes learned from client peers can be sent to eBGP peers, other client peers, and non-clients. Non-client peers. Routes from non-client peers can be sent to eBGP peers and client peers, but not other non-clients. So there is the concept. It actually makes a lot of sense if we were just to draw this out real quick. It's like this. If you have your route reflector, and then you have your edge 1, you have edge 2, and you have edge 3. You form a peering to each one of these guys. So in the configuration, when you do your peering, you're going to say route reflector client, and then over here you would say not a client. You just do a simple eBGP peering between these two. What you would end up doing is for this one here, you have an external peering. So you have edge 4. You do an eBGP peering here. This guy advertises a route. E1 receives it, pops it up here. Route reflector passes it down to here and to here. Right? That's how that works. That's an iBGP client. Non-clients, on the other hand, peers can be sent, routes learned from non-client peers can be sent to eBGP peers and client peers, but not other non-clients. In other words, goes back to what I talked about before, where you can't send an update to a non-iBGP peer, right? So another non-client. So you have E5, right? Come up here, can you send the route to him? You can't. So you can turn off client-to-client reflection and turn off client-to-client reflection. That's an option as well. But if this guy right here is not a route reflector client, if that's not the case here, he won't be able to receive the update. So if he's just doing a regular peering back and forth like this guy is here, he won't be able to receive the update because, well, the route reflector doesn't know to send the update. So the simple thing is just to make everybody a client. Now there are some caveats that go into play with that, but for the most part, if you want to test this one out, be my guest. I would definitely recommend you do that, but in real world designs, almost every time we've done it's a route reflector client. It makes life so much easier. So that is essentially how that will come into play. So the other thing to talk about is route reflector processing. So what we're going to do is, let me see here. Do I want to go? There's some other options here. Yeah, so we'll cover this last little bit here and go from there. So, route reflector update processing. Route reflector processes updates differently depending on what type of peer they come from. So when the route reflector receives routes from its iBGP peers, they are tagged internally as being received from a client peer, and are a candidate to be advertised onto everyone. Again, eBGP learned routes pass to eBGP peers, clients, and non-clients. Client learned routes pass to eBGP peers, clients, and non-clients. And then non-client routes pass to eBGP peers and clients, but not non-clients. Again, if you are receiving a route from a peer that's iBGP but not configured as a client, you're not going to pass it to other clients. To non-clients. So just remember that. When a route is advertised or reflected from the route reflector to a client or non-client, BGP attributes such as the next hop are not updated. Instead, 2 new attributes are added to the reflected prefix, the originator and cluster list. The originator, this is going to be the peer that received the route and advertised it to you, and this is going to be the route reflector's information. So the originator ID is set by the route reflector as the BGP router ID of the neighbor from which it learned the prefix. If the originator ID matches their own local router ID, the route is discarded. Again, that's a loop prevention mechanism. Cluster list contains the cluster IDs of the route reflectors that the route transited through in the network. Unless the BGP cluster ID command is manually configured under the BGP routing process, the default value is to use the router ID of the route reflector. Again, you can change the cluster ID. And when you change the cluster ID, if you've got, say, two different route reflectors, and they both have the same cluster ID, they're going to treat each other as iBGP peers. And therefore, if I send a route, and I'll whiteboard this out real quick. If I am a route reflector, we have R1 and RR2, and they share 1.1.1.1, right? So I have client 1, client 2, client 3. I'm going to peer to each one of these guys. So that would be the logical breakdown. You've got 5 routers, you've got 3 peerings to each client. If I have an eBGP peer here, and I have an eBGP peer here, and I have an eBGP peer here, I'm going to send that up to the respective route reflectors, but they are not going to share it between the two of them. They'll each know about it, but they're not going to share it with each other. Even if I peer to them, they're not going to share it. Now, if I change my cluster ID and I'm 1.1.1.1 here and I'm 1.1.1.2 here, I am going to share it because I had 2 different cluster IDs. So therefore, they're eBGP peer design. So they are going to share information with each other, and it actually gives you, to me, this is the better design. If I'm going to scale, I'm going to scale out using this design because it gives me more flexibility. So with that being said, that is essentially what I wanted you guys to understand. This attribute is used to prevent loops between route reflectors. A cluster of BGP is defined as a route reflector and its clients. When a route reflector learns a route from an iBGP peer and the cluster list includes its own cluster ID, the route is discarded. The route reflector is analogous. Again, we talked about the DR, and in many cases, traffic does not physically transit through the device. The reflector is simply a central point of the network control traffic, but not necessarily an aggregation point for traffic. So you're going to want to keep things in mind when you're dealing with this. So there's some large-scale rules that can come into play with this. So I'll talk a little bit about that now, and then we're going to go through and take a look at deploying some iBGP peers and go from there. So large-scale route reflection. Large-scale BGP design should not be serviced by a single route reflector. Clusters allow redundancy and hierarchy. Cluster is defined by the clients and a route reflector serves. So RRs in the same cluster use the same cluster ID. Per address family pairings, so this avoids fate sharing of services. Having a service provider having an SP provide both global and MPLS services, flopping internet route shouldn't affect MPLS BGP. And you'll see this later on because you can do different address families. So for your IPv4 unicast and IPv6 unicast connectivity, you should not be using the same set of route reflectors for VPN v4 and VPN v6. You should have a different set of route reflectors for that. Inter-cluster peerings. So inter-cluster peerings meaning route reflectors can be client or non-client peerings. Depends on redundancy design. So cluster ID is based on the router ID. By default, all route reflectors are in separate clusters. So same cluster on both routers or not depends on redundancy design. So there are, again, route reflector is based off of the cluster ID is based off of the router ID. So if you set the same cluster ID on multiple devices, they are in the same cluster. Therefore, they will not share routes with one another. That's the big thing you got to remember here. There are some virtual options as well, and I've done this a few times. So the route reflector doesn't need to be in the data path, but can be. It's not going to matter one way or the other. I give you the route, but you forward it through someone else. So you can use iOS XRV, CSR 1000V, stuff like that. Virtual route reflector scale. You no need to install half a million routes in the fib if the route reflector is not in the data path. It's much easier to deal with this when you're dealing with a virtual box with lots of resources that's running inside of your ESXi environment or what have you. It gives you much more flexibility. So I'm not going to get into configuration because of the fact that it's a complicated design, but what I will talk about is configuring route reflection. So route reflector, what I will talk about is the command structure, and the command is actually very, very simple. When you go to set it up, literally all you have to do is type in neighbor, the IP address, underneath the address family, and we'll talk about doing address family specific and non-address family specific configurations. But the high level is going to be neighbor, the IP address, and then route reflector client is going to be the command. That's literally all you have to do, and you do this on the route reflector itself. The clients just peer to a specific IP address, which is a loopback of a device. So now that I've gone through that, and now that I'm at a half an hour, what I'm going to go ahead and do is I'm going to talk about doing, in the next video, I will walk you guys through, because I don't feel like doing an hour-long video. We'll do a iBGP peering full mesh, and then we'll take a look at doing a route reflector design and see exactly how that looks. So there's a lot of information to go through when it comes to that type of stuff, so be cognizant of those details. If you guys have any questions, comments, concerns, feedback, drop a line in the comment section below. If you haven't already done so, please like, share, and subscribe, and I'll catch all of you fine people in the next video.